Welcome to This Explainer. Today, we're diving into one of the most beautiful and honestly revolutionary ideas in the history of quantum mechanics. We're talking about de Broglie matter waves. It's a concept that completely changed physics forever, and I'm super excited to unpack it with you.
So let's kick things off with a bit of a thought experiment. Imagine you grab a baseball and give it a good hard throw, but instead of flying through the air in a normal, predictable arc, it suddenly just spreads out, like a wave rippling across the entire stadium. Sounds completely impossible, right? Like some weird glitch in a video game. But according to a young French physicist named Louis de Broglie, every single object in the universe actually has wave-like properties. Yeah, literally everything. A baseball, a planet, even you.
Part 1. The Quantum Physics Prelude. Let's set the stage real quick by looking at how scientists viewed the world right before this mind-bending concept came along.
For centuries, the scientific consensus was built stone by absolute giants of physics. We're talking people like Isaac Newton mapping out the laws of motion and James Clerk Maxwell defining electromagnetism. Together, their work kept our understanding of reality neatly and, comfortably divided. Up until the early 1900s, physics just felt complete. It was predictable, orderly, and made total sense.
Basically, the universe was split into two distinct teams. On one side, you had matter. Matter was thought to be made entirely of tiny, solid individual particles. You can think of them like microscopic billiard balls. On the other side, you had light, which behaved strictly as a wave, kind of like ripples moving across a pond. So matter is particles, light is waves. Boom, case closed. Or, well, so everyone thought. Right up until Albert Einstein stepped onto the scene in 1905.
Einstein completely shocked the scientific establishment. In his groundbreaking work on the photoelectric effect, he showed that light, which, remember, everyone absolutely knew was a wave, sometimes actually behaves like tiny packets of energy. We call those packets photons. He revealed that light could behave as both a wave and a particle. It was a massive game changer, and suddenly those neat little boxes of classical physics were just blown wide open.
Now this inevitably led to a perfectly mirrored question. It's such a simple thought, but incredibly disruptive. If waves, like light, can sometimes behave like solid little particles, could particles, like the solid stuff making up you and me, sometimes behave like waves? That exact question completely flipped physics on its head and set us up for the next giant leap. Part 2. De Broglie's brilliant idea. And that brings us to 1924, when our young French physicist proposed an almost unbelievable answer.
The sheer scale of his claim was just staggering. De Broglie suggested that every single particle has an associated wave. And he wasn't just talking about bizarre microscopic anomalies. He meant every particle. Electrons, atoms, protons, neutrons, sure. But he also meant baseballs. He meant entire planets. According to his theory, absolutely everything possesses a wavelength. When he first pitched this, a lot of scientists were extremely skeptical, and you can't really blame them. It sounded like pure science fiction. But history would very quickly prove his wild idea right.
Part 3. The famous wavelength equation. So, to really grasp how this works without getting bogged down in complex math, let's take a look at the elegant equation behind it.
Here it is. This simple, elegant equation reveals an incredible truth about our universe. The symbol on the left, lambda, stands for the wavelength. Then, on the right, h is Planck's constant, which is a universally tiny microscopic number. And p is momentum, which is essentially how much mass an object has combined with how fast it's moving. Now, because h is always on the top and is incredibly small, the greater an object's momentum on the bottom, the smaller its wavelength becomes. It is just a strict, beautiful mathematical balancing act.
Let's put that into perspective with a couple of real-world examples. If we compare these objects, the math becomes super clear. An electron has very little mass, meaning its momentum is extremely low. Therefore, its wavelength is large enough that we can clearly observe its obvious wave behavior. But a football? Well, a football has an astronomically higher mass compared to an electron. Its high momentum means its wavelength shrinks down to a size so unimaginably tiny that absolutely no experiment or technology could ever detect it.
Part 4. Proving matter waves exist. Of course, a mathematical theory is really only as good as the experiments that confirm it, which brings us to a historic moment in 1927. Scientists Clinton Davisson and Lester Germer designed a brilliantly simple test. They basically fired a beam of electrons at a nickel crystal. Now, if electrons were purely solid particles, they should have just bounced off the crystal like tiny bullets hitting a brick wall, scattering completely randomly.
But instead, when they observed the collision behavior, they found a diffraction pattern. And diffraction patterns are exactly what waves do when they overlap, kind of like ripples intersecting in a pond. It was undeniable physical proof that electrons actually behave as waves. De Broglie hit the nail on the head.
Now, I want to clarify a really huge misconception here. When we say an electron is a wave, this doesn't mean the particle is physically wobbling up and down like water in the ocean. Actually, scratch that. It's more like a wave of chance. The wave represents the probability of where the particle might actually be found. It is purely a wave of statistics.
This realization was a massive paradigm shift. It became the very foundation of Erwin Schrödinger's famous wave equation and completely overhauled our model of the atom. You know that old image of atoms looking like tiny solar systems, with electrons orbiting a nucleus like planets around a sun? Yeah, we now know that's just not true. The electron exists as a quantum wave, a probability cloud spread throughout space around the nucleus. It is everywhere at once in a state of potential, until we actually measure it. Only when we take a measurement does that wave collapse, and we detect a solid particle in one specific spot.
Which naturally leads us to a pretty fun question. You're probably wondering, if everything has a de Broglie wavelength, why don't you spread out like a probability wave when you walk down the street? Why don't you diffract when you walk through a doorway?
The answer brings us right back to de Broglie's equation. Because your mass is so mathematically enormous compared to a single electron, your wavelength is incredibly, incredibly tiny. We are talking unimaginably microscopic, vastly smaller than even a single atomic nucleus. Because your wave nature is so infinitesimally small, it just completely cancels out at our human scale. This means you, me, and everything we interact with on a daily basis behaves entirely according to the neat, predictable rules of classical physics.
Part 5. Why matter waves matter.
You might think these quantum effects only matter for extremely tiny particles in a lab somewhere, but this microscopic phenomenon actually powers our macroscopic everyday world. Without matter waves, modern electronics simply would not exist. Engineers literally have to account for the wave-like behavior of electrons to build semiconductors. The silicon chips inside your laptop, advanced electron microscopes, the quantum computers being developed right now to solve impossible problems, and yes, for sure, the smartphone sitting in your pocket right this second, all of them directly owe their existence to this one remarkable idea. We essentially harness the wave nature of reality to build the digital age.
De Broglie's discovery transformed science forever. He looked at the established facts, asked one brilliant backwards question, and united matter and light under one bizarre, beautiful framework. It reminds us that reality is far stranger and far more connected than our everyday experience suggests. It leaves us with this profound realization to chew on. When you strip everything down to its absolute core, the solid universe you think you know isn't just made of particles. It's made of waves. So what else about our reality is hiding right beneath our everyday perception, just waiting for the right equation to reveal it? Thanks for joining me on this explainer. Until next time, keep questioning the world around you.